Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, I will give you a short video on probability. I know I have a whole course on probability, but this one is for uh, like beginners. So if you are in a middle school and you start taking few questions and problems about probability and some statistics, and you learn how to find the mean, the median, whatever, and get like a box plot or something. I'm going to touch on one type of problems, and it's common. It's, for example, tossing a coin. Tossing a coin, you know that if it's a fair coin, you get 50% or probability of one half of getting a head and a probability of one half of getting a tail. Also, if a family, are expecting a boy or a girl, just not a twin or a triplet, just one kid, the likelihood that that kid is a boy or a girl is one half and one half. For these types of problems, and even for any other two types of problems, even other types of probability, when the two outcomes of the probability are not equally likely, we still can use my favorite Pascal triangle. Ta-da! Okay. But if it's one half and one half, the probability is extremely easy to find. Let me give you an example and tell you how we solve it. So I'm going to probably go over a couple of examples. Example number one. Let's say part A of it, I would say you randomly select a family of 3 kids. So you know all what you know about the family is that they have 3 kids. You don't know them, okay? And I say, what is the probability that these kids they are 2 girls and 1 boy? Since the probability is one half to one half, like the odds are 50-50, I can very easily select Pascal triangle. Pascal triangle start as, if you haven't watched my other videos on Pascal triangle, it starts with 1, and then every row underneath it, I increase a number. But every row has to start with 1 and end with 1. Okay? And then how do I fill it? You see here, I should have 3 elements. I have 1 and 1. So what's in the middle? You pick the 2 above it and add them up. 1 plus 1 is 2. How do I get that? 1 plus 2 is 3. How do I get that? 15 plus 6 is 21. How do I get that? 15 and 20 is 35, and so on and so forth. We look at the second number. This one doesn't have a second number, so we call it the zeros row. This one has 1 as the second number, so we call it the ones row. Here you get 2, it's the twos row. Here is a 3. Oh, family of 3 kids. So I'm going to use this row. And the row is 1, 3, 3, 1. 2 things we do. You identify, it's up to you. I don't care. I don't care what you do. You can call the left boys and the right girls, or the left girls and the right boys. Okay, maybe pink and blue, even though that's light blue. And what does that mean? Wait a second. The first thing you do, you add the numbers. Of course, that's easy. I can say 1 plus 3 is 4, plus 3 is 7, plus 1 is 8. But what if I am in row 10? Oh my God, how do I add that? No, you don't add them. You say the sum. So if I add those, I will get 2 raised to the number of the row. It's the third row or the threes row, 2 to the third. And if you haven't taken exponents yet, 2 to the third means 2 times 2 times 2. So 3 2's multiplied by each other. 2 times 2 is 4, times 2 is 8. So of course that number is 8. If I am in 7 row, so instead of adding those, I can use my calculator and get 2 to the 7th, which is 128, right? You can try it. Okay. The first row, the first number, notice that my probability would be something over something, but that something is always going to be 8. Always, because there are only 8 outcomes, we call them. This is the probability of getting 0 girl, 1 girl, and when I say 1 girl, it means 1 girl and 2 boys. 2 girls, 3 girls. Which one do I want? I want 2 girls, meaning this guy. It's a 3. So the answer is 3/8. 3 over 8, which as a decimal is 0.375. It's that simple. What is the likelihood that I get 3 boys? It means 0 girls, 1 over 8. What is the probability of getting 3 girls? It's the same, 1 over 8. So, second part say that if you check 8,000 such families, meaning that families that have 3 kids, how many such families do you expect to have 3 boys, 2 boys and a girl, 1 boy and 2 girls, 3 girls? It's so easy. Once you get the probability, you multiply the probability by 8,000. So to solve for 3 boys, meaning 0 girls, I'm going to multiply 8,000 by 1 over 8. 1 over 8. 8,000 divided by 8 is 1,000. So the answer is 1,000 families. 2 boys and 1 girl. 1 girl is 3. So 8,000 times 3 over 8 equals 3,000. 1 boy and 2 girls. 2 girls. It's the same. 3,000. 3 girls. 3 girls is 1 over 8. So multiply by 8,000. It's the same as the top. You get 1,000. Of course, in real life, they will not be exactly 1,000, 3,000, but very close to these numbers. That's the power of what we call the binomial distribution that you will learn later when you take really an advanced course in probability. You will see that there are different probability distributions or families, not families like this, families of outcomes. And one of the most important are the binomial distribution. Now I'm going to give you a question that I gave. Unfortunately, I gave it to 7th graders, so it was a little above their pay rate. But anyway, it should be easy. But what I want you, if you find the answer, to write it in the comment section for me to check. I did something similar to that in what we call the calculation of Burma, and I get a student. I don't know if it's a boy or a girl, okay, but did it very nicely, got the answer correctly, and I'm really proud of them. So this problem, and then I will give you another example of what if the probability is not 50-50, the odds are not 50-50, something else. Problem, or just a problem, not problem 2, that was an example. Okay, I'm going to say, you toss a fair coin. Don't do that at home because your siblings and parents may think you're crazy. And you should be crazy. I mean, if you are watching my videos anyway, because you get it from me, right? Yeah, I think so. So you toss a fair coin. If it's a head, you take a step to the right. See, that's why I said don't do it at home. Or make sure your parents are out. And if you have siblings, they are either sleeping or not, or you lock yourself because they would say, okay, this guy, okay, he lost it. Okay, a step to the right. And if it's a tail, you take a step to the left, to the left, to the left. Yeah, I know. See, I told you we are crazy together. I mean, we form a family of crazy people. So I'm like most likely the age of your grandparents. So you give me a slack, right? Old man, so I can be crazy. No big deal. Okay, now I think I asked the seventh graders, what is the probability after four tosses? No, I'm going to ask you, what what's the probability that after six such tosses, you find yourself where you started? I don't think you need a hint, but the hint is, oh, they have to be an even number of tosses, not an odd number. It's not too much to give away, but maybe it would lead you to the correct answer. Here again is Pascal Triangle, Blaise Pascal, and you can work on it. Now, the second example I'm going to give you quickly, and we'll finish here because really I wanted it to be shorter than that. But example two. So suppose we have, I shouldn't say production line because the probabilities would be very small. So it would, I'll try to make it, okay. Suppose we have an experiment that has two possible outcomes, exactly like tossing a coin or having a boy or a girl, but the probabilities are not equal. Okay, two possible outcomes. Outcome one, we call it success. It doesn't, by the way, success doesn't necessarily in the language of probability and statistic mean good thing. Suppose you are producing some widgets, okay, and you're in your production line, hopefully, because you don't want to go out of business, hopefully almost all of them are good and very few are bad. Okay, maybe a probability of one in 1,000, every 1,001 widgets, you have one that is bad, but you don't know which one, of course, unless you check. So you decided to check because you don't want to send it, to the customer and lose them, right? Or get bad reputation. So in that case, if you can find a bad one, we call that a success, right? Because it's a success because you are not going to send it to the customer. Bad success and good failure, yes. So it depends on what you want, right, out of the outcome. So let's say outcome one, which is a success, has a probability. Let's make some number, let's say 0.6. So the failure F has a probability of 0.4, right? They have to add up to 1. You try this experiment or repeat it. Say 10 times, or let's make it 7 times since we have up to row of 7. And you say, but you told us this is if they are equally. No, I said that, yes, but we'll see how we calculate it. Okay, you try this experiment 7 times. What's the probability of getting, and you can write any number of successes, let's say 5 successes. Yeah, I'm not going only to use Pascal Triangle, but you will see how it's going to help me. The probability of 5 successes, meaning 5 successes and 2 failures, since you are going to have it 7 times, equal. I'm going to go to the row of 7 again. Okay? And then I'm going to say, this is 0 success, 1, 2, 3, 4, 5. So I'm going to write 21, because 21 is the number of successes, expected number of successes out of 128, 2 to the 7. Okay? Notice that what I'm going to do, I'm not going to divide by 128. I would have divided by 128 if the likelihood was 50-50, in which case 0.5 and 0.5, the answer would be like the previous example. I take the number 3 and divide it by 8. I take the 21 and divide it by the sum, which we said is 2 to the 7 or 28. But if they are not equally likely, it's so easy. I'm going to say the probability of success is 0.6, and I'm going to raise it to the power of 5. And the probability of failure is 0.4, and it has to be 2 failures because I tried it 7 times, square. And that's it. That would give me the answer right away. Okay? So if that was 0.5 and 1/2 and 1/2, do you see what would happen? 1/2 to the 5th times 1/2 square, as you learn it from exponents, can be written as 1/2 raised to the power of 5 plus 2, or 1/2 to the 7th, or 1 over 128. That's why it works perfectly. And you don't need to do any exponentiation if the likelihood of the two outcomes, if they are equally likely. But if they are not, just use your calculator and say 21 times 0.6 to the 5th times 0.4 square equals 0.261, roughly 26%. Okay? If I tell you what is the likelihood that I at least get 5 successes, meaning 5 successes or 6 successes or 7 successes, then you would say probability of getting greater than or equal to 5 successes would be 21, that's 5 successes, plus 7, which is 6 successes, 6 successes and 1 failure, plus 1 times 7 successes. And it's not going to be much higher. This is 0.261 to 3 decimal places. If I add to that plus 7 times 0.6 to the 6 times 0.4 plus 0.6 to the 7th, I get 0.42 to 2 decimal places, or 0.420 to 3 decimal places. And that's the probability of getting at least 5 successes, 5 or 6 or 7, still less than 50%, but because these probabilities are close enough. If that was like 80% or 90%, you will see this number would be really large. Okay? And that's basically it. I'm waiting for your answer to this one. And then I may give you another problem. No, that's much harder. Maybe I'll discuss it one time, but I know some of you will say, no, give it to us. We are going to try it. This is really tough. I put this question several times in college for college students, and I don't think anybody got it. So maybe I'll put it here, and then I will tell you, I'll discuss the answer later because I know some of you want to try it. And I'm not going to deprive you from that chance. I don't need to write anything. I'm going to talk to you about it. The question is, I have a biased coin. It's the only coin I have. It's biased. I know it's biased, but I don't know. Biased meaning if I toss it, I don't get 50-50 heads and tails. Maybe the heads get much more than the tails, or the tails gets more than the heads, no matter how many times I try. But I don't know the probability, and I don't care what the probabilities of success and if you call head success and tail failure, for example, I don't know if it's 60-40 or 71.2 and 38.8. I don't know, or 28.8, I'm sorry. I don't know. And I don't care. I shouldn't care. But I want to use that biased coin between two players to get an unbiased result. Meaning, after I'm done with that experiment, I'm going to devise an experiment such that no matter what you check, what you choose, your likelihood of winning is 50% and likelihood of losing is 50%. How? You told us the coin is biased. Yeah, I'm not going to just toss it. No, I have to think of a way that no one can disagree with it. You will end up with a correct result. And please, before you think you're doing it correctly, because I heard this answer a lot from some students, they think statistics, not probability. Meaning they would say, oh, we are going to toss it 1,000 times. For example, if you get 600 heads, we are going to say the probability is 60%, and then what? No, I don't. That's why I said I don't want to know, and I don't care what the bias is. All what I know is that the sum of these probabilities add up to 1. They may be 60-40, they may be 30-70, they may be 75-25, 55-45. I don't care. I want you to design an experiment such that at the end of it, whoever selects a head or whoever selects a tail will have the exact equal probability of winning regardless of the coin. I know it's tough. If you don't get it, don't feel bad. As I told you, I didn't get the correct answer from college students in years. So anyway, but if you think of a way, just let me know and I will respond to you and tell you whether it's right or wrong. And maybe in another session, I will explain it to you and give you the answer if no one comes up with it. And I hope somebody gets it. Thank you very much for watching. Wish you all the best and hope to see you soon. Bye.